Welcome to lesson 6 of chapter 9, year 2 pure maths, and this is differentiation. And today we're going to look at differentiating a function and determining whether that function is concave or convex. Now, you might not know what that means at the moment, but all will be revealed shortly. Nothing much else to say really, other than we're going to be using some differentiation techniques, mainly from year 1. And then we'll obviously apply these new concepts. So please pause the video and have a go at the 4 warm-up questions. Okay, and let's have a look at the solutions. Okay, so for question 1, we have a function, it's a cubic, and we have to find the 2 derivatives. Obviously, you're going to need to bear in mind what this notation actually means. It's really important that we don't get mixed up. So this is, of course, the first derivative. It's not the inverse function. Okay, please bear that in mind. And this is, of course, the second derivative. Okay, let's carry out the first derivative then. So this is just standard year 1 differentiation. So we should have 3x squared subtract 12x plus 9. Okay, there's the f dash x, as we call it. And the second derivative, we simply perform that process again, differentiating term by term. 2 multiplied by 3 is 6. Take 1 off the power, so that's going to be 6x subtract 12. Okay, hopefully there's no concerns over that. Then there's a hence part. Obviously, if it says hence, we need to use what we've already done. It's a really important word in the context of an exam question, particularly. So hence find the x coordinates, perhaps, or coordinate of the stationary point or points. Well, how do we determine stationary points? Well, we simply set dy by dx equal to 0. Okay. In fact, I should write it in the correct way. I should say, so set f dash x equal to 0. So I'm not mixing up notation. So f dash x equal to 0. If we do that, we get 3x squared subtract 12x plus 9 is equal to 0. Because this is an equation, I can divide through every term by 3 or factor out of 3, and note that 3 is never equal to 0, so we can disregard it. So therefore, x squared subtract 4x plus 3 is equal to 0. We can now factorize that, hopefully. So it looks like we're going to have x subtract 1 and x subtract 3 is equal to 0. And just moving up here, so I've got a bit more space. So x is equal to 1, or x is equal to 3. So we've just determined or deduced that there are 2 stationary points, okay, when x is 1 and x is 3. We now have to determine the nature of these stationary points. Okay, we now know that there's 2 of them. So when x equals 1, let's see what happens. So how do we determine the nature of the stationary points? Well, now we're going to use the second derivative. Okay, so f double dash of 1, we sub 1 into the second derivative. We get 6. Put that 1 in there. Okay, and now we're going to subtract 12. So that's going to equal negative 6, which is less than 0. And remember, it's the sign of this value that is important. If it's negative, please remember that that indicates it's a maximum, which is the nature. Okay, the nature means that is it a maximum, a minimum, or a point of inflection? Okay, let's try x is equal to 3 now. So we do f double dash of 3, which is, of course, 6. Put the 3 in. And then subtract 12, which is, of course, 18. Subtract 12, which is positive 6 this time, which is greater than 0. And if it's positive, almost counterintuitively, perhaps, I don't know what you think about that, that is going to be a minimum point. Okay, so we have the stationary points at x equals 1 and x equals 3. And we know that when x equals 1, we have a maximum. And when x equals 3, we have a minimum. Now, I'm going to transfer a lot of this information over to question 2 here. The diagram below shows the graph y equals f of x, and it's the same f of x that we've just been working on. So this is what the cubic actually looks like. And we're asked to sketch on the same axes the graph of the gradient function. So recall that the gradient function, which we worked out, is right here. So we're going to have to sketch this graph on the axes that we've been given. Now, if we just have a look at that, we've got a lot of information that we've already deduced. We know it's a quadratic, first of all. We can see that it's a quadratic. Oops, don't want to use that. Quadratic, so it's going to be a U-shaped quadratic because we have a positive coefficient here for x squared. So positive x squared means it's obviously a smiley face, as we say. Okay, positive 3. It's got a y-intercept at 9. And we also know that if we look at the x-intercepts, we have x-intercept at 1 and 3. In other words, the gradient is equal to 0 at 1 and 3. So we know quite a lot about it. So as long as we transfer that over to our sketch, then we're in good shape. Now, notice something interesting. Okay, we already deduced that at the point where x equals 1, we have a maximum. Okay, we saw that here when we subbed in 1. So x equals 1, we have a maximum. So this must be the point where x equals 1 right here. So I'm going to just indicate that on the sketch. So at this point here, we must have x equals 1. Similarly, we know that when we sub in x equals 3, so f dash 3, we get a minimum point. So this must be a minimum. And it's also where the graph seems to touch the x-axis. So at that point there, we know that this point must be 3. Now that's interesting because that clearly that coincides with where our gradient function crosses the x-axis, as we can see at 1 and 3. So that's the relationship between the function itself and its gradient. Where you have the stationary points is where your gradient function is going to cross the x-axis because the gradient function has to be equal to 0 at those points. So I'm going to have a go at sketching this. So it's going to be something like this. I'll do my best. It's not too bad. Now, you can also, this infers many other things. We've also got a situation where the gradient function is going to intersect your original function as well. And that would be a differential equation type of situation, which we're not going to look at. But I think that will do. I know this is going, the y-intercept is obviously going to be at 9 somewhere up here. Okay, but I think that will do for our sketch. So that's the relationship between the function and its gradient. Okay, so I hope that makes sense. Now moving on to question 3, we've got two curves, y equals x squared and y equals negative x squared. I think it's pretty obvious which one's which, but we'll label them anyway. So this is going to be y equals x squared, and this is going to be y equals negative x squared. Okay, simply because the coefficient of the x squared determines the orientation of the quadratic, whether it's a U shape or an N shape. Right, now there's several things we're going to infer from this once we've done some differentiation. So completing the table, if I differentiate x squared, hopefully that won't be too taxing. It's one of the first things we ever did in calculus. So that's going to be 2x. And if I calculate the second derivative of that, just differentiate again, that's of course going to be 2. Applying the same idea to minus x squared, we're going to have negative 2x. And of course, negative 2. So we can see in the first case where we have y equals x squared, we have a nice positive value for the second derivative. Okay, and for the second case, negative x squared, we have a negative value for the second derivative. And that was inevitable because we only have one stationary point on a quadratic, which means that if there's only one, it has to be a maximum, minimum, or an inflection. So there's no variability, which means that the second derivative must be constant because it will fix the stationary point as being either maximum or a minimum. Okay, you can't have multiple maximums and minimums when you have a quadratic. There's only one. So let's just have a look, and maybe we could label this on our diagram here. So we can see here that the second derivative, d2y by dx squared, is negative, is less than 0. And in this case, d2y by dx squared is greater than 0. So that's interesting, isn't it? So we seem to have shown that, and we've explained why that would be in previous lessons, probably in year 1 as well. So that's that. So we're going to use these ideas later. Now for question 4, we're given y equals the natural log of x, and we have to find the second derivative. All right. So in this case, if I just write out it's a standard result, this. So dy by dx, standard result is 1 over x. Okay. Now, just bear in mind that this is, of course, x to the power negative 1. Okay, we need it in index form because we're going to have to differentiate it again. So therefore, d2y by dx squared is going to equal minus x to the power negative 2, which is, of course, negative 1 over x squared. All right. Now, for part B, it says hence prove. So that word hence again, that the second derivative is always, always negative for all x. Now, I'm just going to stress something here that wasn't included, that the x is, of course, it can't be equal to 0. Okay, we cannot sub 0 into that because it's not defined. Let's see if we can prove this. Well, if we look at the derivative that we've got, this is a standard proof, really. You've probably done things much more complicated than this. And the key for positivity is, of course, that x squared, or any squared number, is always positive. So squared numbers are always greater than or equal to 0. So if x is non-zero, but it's also a real number, then x squared is going to be greater than 0. That is just a fact. Okay, positive numbers are always positive. Okay, and we'll exclude 0 from this argument. So therefore, if I do the reciprocal of that, the fact that I've reciprocated it doesn't matter. It's still going to be positive. Okay, and it's still going to be defined provided x is 0 is not allowed. Okay, which I should have stressed in the notes, so I apologize for that. Okay, just going to stress that again. Now, because we've got 1 over x squared, it's not quite the same as our derivative. We need to change the sign of both sides. So therefore, minus 1 over x squared. Okay, if we change that into a negative number, this has to be strictly less than 0. Okay, now we've got our statement. That is the same as the second derivative, so therefore d2y by dx squared must be strictly less than 0 as required. All right, so that's just something to bear in mind. Just keep an eye on these squared numbers. Note that they are always positive. All right, so we're going to have a look at the concept of concave and convex. Now, I'm going to use some analogies here. We've got a concave mirror and a convex mirror. So as it states here, if an object is concave, it's a surface that curves inwards, such as the interior of a sphere. Okay, and if you'll notice, if we go from left to right, as I'm going to do now, on this surface. So this is like a concave mirror with the gray part is the actual mirror part. So if we go that way from left to right, now you'll notice that we're traveling clockwise. Okay, so we're moving in a clockwise direction, okay, along the surface. So that's an idea of what concave actually means. And also, if we look at the alternative, the counterpart to that, the convex, as we move from left to right. So I'm just going to write those on again, and I encourage you to do the same as well to get the concept clear. Okay, we have a convex curve. If I move along that surface, you'll notice that this time we're moving in the opposite direction. So we would be moving in an anti-clockwise direction. All right, so there's two key properties there. If you're concave, it's the arch shape where you're moving in a clockwise direction along the surface, and if it's convex, you're moving anti-clockwise along the surface, okay, in a U shape. So if we transport this analogy or translate it to mathematics, and we've seen a concave curve and a convex curve already. All right, so this is the concave curve, because if I start from left to right and I go all the way around the curve, I'm moving my pen in a clockwise direction. All right, so it's moving in a clockwise direction. Okay, so that tells me that this is concave. All right, if I grab my highlighter again, if I go from left to right, so I'm going along my curve like this, you can see the opposite direction. Okay, we are now moving in an anti-clockwise direction along the curve. So this is what convex means. All right, so those are the key properties. What did we see mathematically that determines this? Because obviously we won't always have the diagrams to help us. What mathematically is happening? Well, we saw in a clockwise concave curve that this is a maximum. Okay, it's absolutely clear to us from this situation we have a maximum. And what do we know about maximums? Okay, we might not always have a maximum, because you can move clockwise along a curve and not achieve a maximum. Perhaps we'll find out later. But we can tell that the second derivative of a maximum, okay, is kind of opposite to what you think. Is always negative. Okay, and here in the convex situation, we have a minimum, and the second derivative is the opposite, as you'd expect, is always positive. Okay, and there's I've taken a photograph. Well, I'm not taking the photograph myself, but we have a photograph here of a cave. So say concave looks like a cave. So I'm trying to imagine there's the arch of the cave there. It is indeed concave. Anyway, so I hope that makes some sort of sense. So let's have a look at some examples applying these definitions. So let's have a look at these two examples. Are they concave or convex, essentially? And we've got quadratics. So first of all, we take the first derivative. And again, please do that. If you know the idea and you're confident with it, just go ahead and do it. If I take the first derivative, okay, so 3 multiplied by 2 is 6. Take 1 off the power, subtract 1, okay, and then the constant term is gone. And then if we take the second derivative, d2y by dx squared, we know that this is, of course, going to be 6. We can now apply our knowledge now, so we know that this is greater than 0, which implies there's going to be a maximum. Sorry, I beg your pardon, a minimum. But more than that, Okay, more than that in this situation, because it's a minimum, we know that this, of course, is a convex. Okay, so convex. Now remember, the minimum looks like that. If we go around the shape from left to right, we're moving in a anti-clockwise direction. Okay, so there's all these little pieces we can put together just to explain it. All right. Okay, so that's convex. Now, if we look at example B, again, we'll just do the first derivative. So dy by dx. Okay, and you can see what's coming, I think. So we've got 5 subtract 2x, like that. Then we take the second derivative, d2y by dx squared. So all this is doing is it's basically telling you, yes, once you've got the second derivative, you can determine the nature of your stationary points, but we can also now say whether a curve is concave or convex. So second derivative is -2. Obviously, this is negative, which implies that we have a maximum. Okay, we don't know where the maximum is, but we know there is a maximum. We'd have to find out where the stationary points are. And also, going back to the shape, because it's a maximum, it's going to be shaped like that because it's a quadratic. This is concave because it looks like a cave. And perhaps more precisely, if we go from left to right, we're going to be moving in a clockwise direction. Okay, so there we go. So there's 2 quite simple examples. So that's quadratics. Now we need to extend this idea to more general curves. So the question that is hopefully on the tip of your tongue, based on what we've done, it is given here. So are curves with more than one stationary point or no stationary points concave or convex? So we've established the quadratics have minimums and maximums, so they must be concave or convex. Not in that order. So let's have a look at some more general cases. And this is where the second derivative is going to really help us. Okay, so here I've got 3 examples where we don't necessarily have stationary points at all, or we have more than one stationary point. Now, as stipulated here, because this is the key to this concept. Okay, talking about concavity and convexity, I think that's a word if there is no stationary points. So the first case, we've got e to the x. Now, e to the x, as you know, has very special properties. Okay, if we take the derivative, which we can do here, we're simply going to get e to the x back. Okay, that's its unique selling point, its key property. Also, if we differentiate it again, we still get e to the x. So the question is, what's going on? Is this concave, convex? What can we tell from that second derivative? Well, it depends on our domain, really. Although not so much in this case, but in some cases it will. So if we let x be any real number, which we can for e to the x, you can plug in any number you like, and you can raise that that input with the base e and get a value back. So that's not a problem. So if we have all real numbers, you'll notice from the graph, okay, the range of e to the x is positive. Okay, absolutely key. So we know that y, just undo that, y is always going to be greater than 0. And remember, there is an asymptote at y equals 0. Okay, so just bear that in mind as well. So this is important. So in other words, if the range is greater than 0, that means that e to the x is greater than 0 for all x that are real numbers. Okay, that's its property. So that means that my second derivative and the first derivative, but we're focusing on this, must be positive for all x that are real. Now, if we go back to our definition, if you have a positive second derivative, well, what does that mean? Well, we could also try looking at it a different way. If we have a positive second derivative, using the quadratics as an analogy, positive second derivative would mean, so I'm not very dexterous with my pen today. Positive second derivative would mean that it would be a minimum, wouldn't it? Okay, d2y by dx squared. So that's a minimum. Now then, what about this? Because clearly e to the x doesn't seem to have a minimum, okay? It's approaching 0, and there's a bit of an arc because it's approaching 1 round about here, but it doesn't actually seem to have a minimum. So what's actually going on? Well, we can just say that for all x, what's going to happen? Which direction am I going to be going in? If I use my clockwise, anti-clockwise rule, if I start here at negative infinity, if you can start there, and I go all the way along here and round, which way am I going to be going? Well, I'm going to be going in the same direction forever, okay? I'm always going to be going from left to right in the anti-clockwise direction. Always. I'm always going to be going anti-clockwise. Okay, so you can tell, even though there's no minimum, if I use the clockwise anti-clockwise approach to this, that must be a convex curve. Okay, it's absolutely essential. So I'm going to make it look really important. It's convex. Okay, the reason it's convex is not because it has a minimum. We've just established that's not the case. The reason it's convex is because that second derivative is greater than 0 for all x. Okay, and when we use our clockwise, anti-clockwise technique, we know that we will always be going clockwise. I'm going to be going vertically straight upwards, but that's still technically clockwise. Okay, because I'm traveling vertically. All right, from left to right, I've gone up from a low position to a high position, so that means I'm going anti-clockwise. Right, so let's move on to the next example. 1 over x, and let's have a look at the derivatives here. Well, we just write this first of all in index form so we can differentiate a little bit more easily. Well, if I differentiate that, I'm going to get minus x to the power -2. Just be careful subtracting the powers, which is of course -1 over x squared. All right. Now we know that that's always going to be negative. We had a similar case with the log graph. That was the second derivative of the log graph, wasn't it? But now we have to differentiate that again. So differentiating again, we've got negative times negative, which is positive, 2x to the power -3, which is of course 2 over x cubed. Now then, when is this positive or negative? Well, this is difficult to say, isn't it? Now, if you look at the diagram, we've got two branches for this graph. So looking at the diagram, we'll start with the diagram first this time. If I look at the lower branch, if I go from left to right, looks like I'm moving downwards. Now, if I'm moving downwards, of course, in this direction, I'm going clockwise. Okay, but if I look at the second branch, I move from left to right, it's a different story, isn't it? Okay, I'm now moving anti-clockwise. So what's going on? Can a curve be concave and convex at the same time? Well, the answer is yes. Now we need to consider when is, how do we go back to the second derivative and deduce when there is a switchover between being concave and convex. So if I'm moving clockwise, we know from what we saw previously, this is concave here. So we know it's concave because it's going clockwise, and this is convex. But how can we show this mathematically? So going back to the 2 over x cubed, let's have a look at the 2 possible cases. So we have 2 over x cubed. Now, this would be positive if, now I'm gonna hopefully try and convince you. Rearranging this is going to be difficult, okay? Because it's an inequality with a 0 in it, and if I cross multiply, I'm going to get absolutely nowhere. But if I have a positive number in the numerator on the left-hand side of this inequality, so here we've got a nice positive number 2. Okay, so that's a start. We know this is positive. And if I want to generate a positive number, then I know that this is going to have to be positive also. Okay, so that in that sense, I can draw a conclusion. I can now say that this is going to be true if x cubed is greater than 0. Okay, so that's when it's going to be positive. Now, if x cubed is greater than 0, that automatically means that x is going to be greater than 0 as well. Okay, and it's technically what we call an if and only if statement. So you can run that in both ways. If x is greater than 0, then x cubed is also greater than 0. But that's something else. So we can now show that we can get a positive value for x, or sorry, I beg your pardon, a positive value for d2y by dx squared if x is positive. All right, now that seems to fit in with what we discovered earlier. So we know that at this part, when it's convex, d2y by dx squared is positive. Okay, and you get that anti-clockwise direction, don't you? Okay, because it's a minimum. If it was a quadratic. Now, conversely, if it's concave, d2y by dx squared would have to be negative. That would mean that x would have to be less than 0 in that case. Okay, so you can see where the changeover is. The changeover is at x equals 0. So when x is less than 0, that's the case. When x is greater than 0, that's the case. But you can deduce that algebraically by looking at the numerator and the denominator in a situation like this, where you have a positive numerator. To generate a positive value, you have to have a positive value here. And if you want to generate a negative value, you would have to have a negative value in the denominator. So I hope that makes sense. And now we're going to have a look at situation number 3, where we have a cubic. And we'll just quickly differentiate this and get straight to the point. So differentiating this, we have 3x squared, subtract 12x plus 9. Okay, this is the one we saw earlier. Now then, we deduce where the stationary points were. We had x equals 1 and x equals 3. Okay, so we had that on labeled on our diagram, and we also drew the graph of the derivative as well. Now, if I differentiate again, I'm going to have 6x subtract 12. Okay. Now then, let's see if we can put this concave convex idea to some use here. If we consider what happens to the second derivative, we've actually got an equation we can solve here. So when we have a d2y by dx squared is greater than 0, that means that 6x subtract 12 would have to be greater than 0. So that means we've got a range of values of x for which d2y by dx squared is positive, i.e. when the curve is convex. Okay? So therefore, x would have to be greater than 12 over 6, which is 2. Okay, now that's interesting. Now, if we look at the alternative, and I've just realized I'm taking up a lot of room with this, so I'm just going to box some of this off. So if we do d2y by dx squared is strictly less than 0, then we have the opposite situation. So we would have x would be strictly less than 2. Okay, so in situation 1, which I've just talked about here, where d2y by dx squared is positive, this would be where you're going anti-clockwise and you get a convex shape. And over here, this is where you'll get a concave shape. Now, we've shown it algebraically, but wouldn't it be good to see how this plays out on the diagram? Well, when x equals 2 is actually a really, really special point on this curve. It's right in the middle between the maximum and the minimum. And it's a point where you have 0 convexity and 0 concavity, okay? It's not curved in any sense. It's perfectly straight. All right. So it's right where there's a crossover between convexity and concavity. And you'll see this as we use our clockwise anti-clockwise rule. So if I start on the left here and I go towards the right until I get to that point where x equals 2, and I'm just going to label it as well as x equals 2 here, you can see that I've just traveled in a clockwise direction. Okay, up to where x is equal to 2. Now, if I'm traveling clockwise, obviously we've established what happens. This means it's concave. All right, this is the concave bit here. So this is when x is strictly less than 2. I'm going clockwise and it's a concave curve. Now, when I get to x equals 2, this is where we have the switch over. So now, look what happens. I'm going to go in the opposite direction in terms of clockwise and anti-clockwise. I'm now going anti-clockwise, which suggests that I'm now in this portion. So this is where the second derivative is positive, x is greater than 2, and the curve is convex. Okay, so we've looked at 3 different cases there. So now we can apply this to some more rudimentary examples. Okay, so before we do the examples, we're just going to put all this into a nice, neat definition. Okay, so it says here, using the second derivatives, we can determine whether curves are concave or convex or not. All right, and a function is f of x is concave on a given interval. That's important because we have to specify the domain. Okay, that's what that means, on a given interval. So we've been looking at all real numbers so far. If and only if, that's the if and only if statement I was mentioning earlier. It's a statement that runs both ways. If and only if the second derivative is strictly negative for all values of x in that interval. Okay. Now a function f of x is convex on a given interval if the opposite is true. If that second derivative is strictly greater than 0 or positive on that interval. Now, what we haven't defined is that point where there is the changeover between being convex and being concave. And this is what we call a point of inflection. Okay, and it's where the second derivative is equal to 0 and f of x changes sign. All right, so this is your point of inflection. So you can see here that as I go clockwise, this is where we are concave. So going clockwise along the curve, this must be concave. So that means that the second derivative is negative. And then we switch over. Okay, and now we are going anti-clockwise. Although we're still traveling in the same direction, but we're now, i.e. from left to right, but we're now going anti-clockwise, and this is where we are convex. Okay. Right. So I hope that makes sense. Now, let's have a look at some worked examples. So we're going to be using some notation for intervals. I'll explain more about that in a moment, but hopefully that concept is pretty clear. So it builds on what you know about maxima and minima, particularly with quadratics that you learnt in year 1. So for worked example 1, we have a function f of x, which is a cubic. And for part A, we have to show that f is concave on the interval -2 up to but not including 0, and on the interval 1, 3. Now, I just want to say a couple of things about these intervals before we actually start the question. So if you see this notation here, where you have the square brackets and the curved brackets, and similarly here where we have 2 square brackets, we can write out the interval in a slightly different way. So when we have the interval -2, 0, I'll just call this one number 1, and we'll call this one number 2. Just want to explain what this means. So for number 1, when you have a square bracket or a straight bracket, that means that -2 would be included in the interval. So we could write this as -2, okay, included, okay, but up to, but not including 0. And that's represented by the curved bracket. So the straight bracket represents inclusive and curved bracket represents not inclusive. So similarly for interval 2, we've got 2 straight brackets here. So this means that 1 and 3 are included on that interval. So this means that the interval described there is going to be x between 1 and 3 included. Okay, so just a bit of word on notation there. And I'll just stress that. So that would be that straight bracket and sorry, square brackets on both sides there. Right, so for part A, we have to show that f is concave on the 2 intervals. Well, the first thing we need to do is to find the second derivative. So to do that, we've got to differentiate twice. So if we differentiate twice, we're going to have 3x squared, subtract 4x, subtract 4. Okay, is the first derivative. And then if we differentiate again, we've got f double dash x is going to equal 6x subtract 4. Excuse me. So that's the differentiation done. Now we have to deduce what's going on. Well, just as a note, we now know that the second derivative, if f double dash x is positive, okay, so you get a positive value, we know that this is analogous to having a minimum, all right, but it's also the same. If it's a minimum, that also means that it's convex. Okay, and conversely, if we have a strictly negative second derivative, this means that we have a concave function. Okay, so that's 2 important pieces of information there. Right, now we know that, we can deduce what's going on with our second derivative. Now, the second derivative, as luck would have it, is a really nice, simple, straight line graph. Okay, so I'm just going to see what happens to this straight line graph. I'm just going to draw a little diagram so we can see it. So if I draw a diagram here, so we've got the x-axis here, got the y-axis here, or f of x. Okay, so we've got 6x subtract 4. So I'm just going to put the graph on here quite simply. So it'll be something like this. Okay, so this is going to be y is equal to f double dash x, which of course is equal to 6x subtract 4, and then we can put some key points on our graph, can't we? So we know the y-intercept, of course, is at -4. Okay, and we're going to have an x-intercept at 4/6, which is, of course, going to be 2/3. All right. Now, you'll notice we're interested in 2 intervals, okay, for this. Now, the first interval is from -2 up to 0. Now, the answer is sort of staring at us, isn't it? From -2 up to 0, I'll put it about here, but I'll just indicate them on the diagram. So -2, let's put that about here. And of course, 0 is where it is. In fact, I'll put it on the right side of the x-axis. So -2 to 0, we can see that f double dash x is definitely negative. Okay, now we can prove this algebraically, of course, because we can say f double dash x is linear and increasing. Okay, it's an increasing function because it's got a positive gradient. With m equal to 6. Now, we can show that this, because we know that from the linearity and the gradient is positive, we can now sub in -2 and 0 and show that we get negative values. So therefore, if we do f double dash of -2, okay, so we can deduce what the y values would be, we would get 6 lots of -2. Subtract 4, which is very negative indeed, isn't it? So that's going -12 minus 4, which is -16. Okay, so that checks out. That's negative. And if we put in f double dash of 0, but remember 0 is not included. So anything less than this, 6 lots of 0. Well, we've already worked that out. It's the y-intercept, but we'll do it anyway. -4, which is also negative. Okay, so we've just shown that because the second derivative is negative on the interval, which we'll state here, negative on -2 up to 0. That means that from the property that we described earlier, the concavity property, we've got negative second derivative. That means it's concave. Okay, now for the second interval, we do the same thing. So if you can see from the diagram here, which is really useful in this situation, we're going to look between 1 and 3. Now, because I've already found out where the y-intercept is, sorry, the x-intercept is at 2/3, we know that 1 is slightly further along, isn't it? So I'll just indicate that on here. So it's going to be about here. Sorry about my scale. And 3 is going to be about here. We can see it's definitely going to be positive. No question about it, but let's just show that algebraically. Okay, and we've already said that f double dash x is linear and increasing. So we just have to put the numbers in and show that we get positive values. Okay, so I'm just going to partition that. F double dash of 1 is going to be 6 multiplied by 1. Okay, subtract 4, which equals 2, which is positive. Okay, that's what we want because we're showing convexity, or that it's convex. And f double dash of 3, maybe I've made those words up, I don't know. 6 multiplied by 3, they seem right though, don't they? Subtract 4, 3 6s are 18, subtract 4 is 14, which is again very positive indeed. It's increasing as you'd expect. So this is convex. Now, you've got to be careful with that. I had to state, I mean, the important step there is to state clearly that f double dash of x is linear and increasing. Okay. Now, if you don't do that, if you just assume that it is, and it's not the same question, and there may be a turning point in your interval, then you can't obviously state that your function is purely increasing because you don't know. Okay. We know this because I've sketched it and we know it's 6x subtract 4, which is an increasing function. So you need to be clear about that before you just plug the numbers in. Okay. I'll just explain to you what I mean with it with a diagram. So for example, if you had an interval between here and here, and let's say it was 1 and 3 again, and you said f of 1 is positive and f of 3 is positive, therefore it's always positive in that interval. Well, you'd have a problem if your graph was doing something like this, okay, when clearly it wouldn't always be positive, and if that was your x-axis. So you have to be very, very careful when you're showing that something is always positive on an interval. Right, anyway, moving on to part B. This is really simple, and in fact, we've already done it. We just have to find the x-coordinate of the point of inflection. So for part B, we just simply set 6x subtract 4 equal to 0. All right, because that's where it's neither convex nor concave. And we've already done it because we found the x-intercept. So therefore, x is going to be 2/3, 4 over 6. Okay, so I hope that's clear. All right, so just be careful and make sure you're clear about what type of function your second derivative is before you start drawing conclusions about whether it's going to be purely positive or purely negative on a given interval. Now for question 2 or example 2, we've got an equation here, which I'm just going to write out again. Y is equal to e to the x cos x. Now it's defined just on the interval from 0 up to pi, including both. Okay, so that's going to be important. It's not all real numbers. And we have to show it has 2 points of inflection. So obviously we need the second derivative. So let's start differentiating now. Actually, before I do that, you'll notice we've got the product of two functions, e to the x and cos x. So we're going to have to use the product rule here. So that's 1 and that's 2. Okay, I'm hoping it's obvious when to use the product rule now when you've got two different transcendental functions or a polynomial and a trig function or something like that. Two completely different things multiplied together. We're going to have to use the product rule. So let's set up our product rule. So we're going to have 1 and 2. We'll have diff 1. And we will have diff 2. Like so, and just write them all in. So 1 is e to the x and cos x is 2. Now we have to differentiate both of them. Well, the derivative of e, really simple, is just itself. And cos, standard result, again, goes to negative sine x. And now we start from function 2 and cross multiply and add. And that's your product rule. Right, let's go. So dy by dx is going to equal cos x e to the x. I'm going to put the e to the x first, so it doesn't look like cos of x e to the x. There can be a confusion there. Now we're adding, but we have a negative sign here. Just be aware of that. It's negative. When we add a negative, of course, it's a subtraction. So just got to be careful. So it's going to be subtract e to the x sine x. All right. So that gives us our derivative. Now, we need to find the second derivative. So looking at our solution, it looks like we're going to have to differentiate this again using the product rule again. Now, it's up to you how you do it. You'll notice we've got e to the x cos x back. So I get that one for free. It's just going to be the same thing. But what I can do now is I can differentiate the second term of this using the product rule again. So I'm going to have to find the derivative of this. Okay, if you don't like that idea, we could always just factor it all out. In fact, maybe I'll do that instead, just so it doesn't look quite as confusing. So if I just factorize the whole thing, so it's going to be e to the x multiplied by cos x subtract sin x. Had a slight change of plan there. Okay, so for the second derivative, we're going to call this one 1. We'll call all this 2, and we'll write out our product rule again. Won't have enough room if I put it there. Planning ahead. So diff 1 and diff 2. Right, let's write them in. So the two functions are going to be e to the x and cos x subtract sin x. I mean, don't worry. I mean, you can do it whatever way you like, really. It's completely up to you, as long as you're consistent. You apply the rules correctly. Derivative of e to the x, of course, e to the x, and cos x minus sin x, two standard results term by term, negative sin x, and the derivative of sin x is, of course, cos x, but because it's subtraction, subtract cos x there. All right, and then we now apply our product rule again. Let's see what we get. So dy by, no, it's not, it's d2y by dx squared. It's the second derivative. Okay, that's going to equal e to the x multiplied by cos x subtract sin x. Okay. Now, I'm going to put a plus in here, plus e to the x. And then we've got negative sin x, negative cos x. Now, that looks pretty complicated, but we've got some same terms. There might be some cancellation here, positive and negative signs. It'll be worth expanding all this. So we've got e to the x cos x subtract e to the x sin x, expanding the first bracket, subtract e to the x sin x again, and then subtract e to the x cos x. And if you do it a different way, you just verify that you get the same as me. And do we have cancellation? Well, yes, we do. We look here, we've got the e to the x cos x here is going to cancel with the negative e to the x cos x there. And we don't have any more cancellation. We've actually got minus 2 e to the x sin x after all that work. So it's going to equal minus 2 e to the x sin x. Okay, so there's our second derivative. So we've done well. Now we have to find out what or where are the points of inflection. Apparently there's 2, because it specifies in the question clearly that there's 2. So we're expecting to get 2 points of inflection here. So remember, at points of inflection, I'll just make a note of this. Points of inflection, we now know, or we know from what we've talked about, d2y by dx squared must equal 0. So we set our second derivative equal to 0. So therefore, minus 2 e to the x sin x is equal to 0. And remember, we're only interested in any solutions that occur between 0 and pi included. Okay, so I'm going to write that interval down using inequalities. So that we're interested in from 0 up to and including pi. Okay. Right. Now to solve this equation, we've got a product of three numbers. We've got -2. Now I'm hoping you'll realize that -2, if we're multiplying anything by -2 and the answer is 0, the -2 itself can't equal 0. So the -2 is gone. E to the x is the second term, or is the second factor. So -2, that can't equal 0. E to the x here, does that ever equal 0? Well, the answer is no. It has an asymptote at y equals 0. It's always positive, so that can't happen. So the only way this can hold is if sine x itself is equal to 0. Now then, if we solve this as a simple trig equation, we should find that there are two solutions on the interval from 0 to pi. Okay, now if we do that, you can do this on a sketch or a cast diagram. It's up to you. I'll do a cast diagram. Do both if you want to. It's completely up to you. So C, A, S, and T. And I know it's not authentic, but we can put the 0 degrees. We'll pretend it's positive, although it's got no sign, but you'll see it won't matter in a moment. If I put that on there, in all and sine, and I'll just put, I know this is not true at all. 0, if I do inverse sine of 0, that's 0 degrees or 0 radians. And I also get 0 radians there. Okay, so I'll just put that step in. So the principal angle is x is equal to 0 radians. You can check that on your calculator. So that means, of course, that x must equal 0 or pi minus 0, which is, of course, going to be 0 or pi. And you'll notice that the solutions, the interval was chosen very, very carefully, because if 0 and pi were not included, there would not be 2 points of inflection. Okay, so if 0 wasn't included, there'd only be 1 point of inflection. And similarly, if pi wasn't included, there'd only be 1 point of inflection at 0. Okay, so that's where the 2 points of inflection are. Okay, so I think that concludes the example. Have a go at the questions, and I hope we get on right with those. Thank you very much.